One. I am Duc Anh Nguyen from Biophysics Center Institute for Chemical Research, Kyoto University. Now I would like to present my research entitled SPARE, a SPARE hypergraph network for learning multiple types of latent combinations to accurately predict drug-drug interaction. Here is the outline of my presentation. First of all, I would like to introduce the drug-drug interaction prediction problem. And then I present our proposed method to solve the problem. The next part is experiment and the conclusion of our work. So let's start with the introduction to drug-drug interaction prediction. So here is the drug-drug interaction prediction. We start with the drug-drug interaction data. In the drug interaction data, we have a drugs and side effect. Drugs consist of drug information with chemical feature and biological feature. For example, protein targets. And side effects are unwanted reactions of human body due to drug use. For example, headache or nausea. And we have a known interaction, which are pair of drugs with corresponding side effects. And the task is we would like to predict all side effects for each pair of drugs. And I would like to present an overview of existing work for drug-drug interaction prediction with a focus on the graph-based methods. So from DDI data, a commonly used method is to formulate DDI data in form of a DDI graph. So what is DDI graph? DDI graph is a graph where drugs are nodes on the graph and acids are the interacting pair of drugs, and side effects are the label of the acids. And each side effect is represented by one hot vector and also considered as a label. So the idea of learning on DDI graph is to propagate and learn the drugs information through the graph. But one problem with the DDI graph is that interactive side effect has a complex relationship. For example, co-occurrence of different side effects. By representing as a label, we cannot effectively solve the relationship between side effects. So in order to solve this, we already proposed to bring DDI graphs to DDI hypergraph. So what's different? We change the side effect one hot vector into a node, into a graph. So now the graph becomes hypergraph, and each hyperaxis, instead of only contain 2 drug nodes, now it contains 3 nodes, 2 interacting drugs and 1 side effect. So I emphasize that each pair of drugs may depend, belong to several different hyperaxis. And from the DDI hypergraph, we can propagate and learn both the drug and side effect all together, not only drugs on the DDI graph. And by doing this, we expect that we can propagate side effect all together by throwing nodes on the DDI hypergraph, and we can learn side effect relationship also. And the idea in detail. So we can bring project the node on the DDI graph in the latent space, and each drug and side effect is represented by a latent vector. And we further proposed assumption that is each side effect is caused by a single combination of of latent feature of drugs. And from this latent space, we will predict side effect. That is, if the side effect is matched with the combination of the drug latent feature, then we have an interaction. So what is the remaining problem of the existing works? So we read 2 problems. The first one, existing work do not learn the multiple types of latent combination. So what does it mean? In reality, each side effect may have a different latent mechanisms, not a single one. So each kind of latent mechanism can be understood as one combination of latent feature of drugs. So we may have several combinations. But previously, we only assume that they are a single combination. Actually, this single combination is the union of all elements of the combination. And now we apply to learn the model that can learn the different combination. And the second problem is data sparsity. So let's imagine drug and side effect data in form of a three-dimensional tensor. And for the larger data, the non-interaction data is about 97.6%. So we have a very sparse data. And learning in spare data is normally hard. So we apply to propose some method to deal with it as spare data. And in order to solve the two problems, we propose spare methods, the solution for the arrest problems. So our idea is to use an autoencoder framework. With input is the DDI hypergraph and the drug feature. And the output of this autoencoder is the reconstructed the DDI hypergraph with the predicted type assays. And our idea is, again, to project the input into a latent space with a drug latent feature and side effect latent feature. And what we do on this latent space? For the first problem, we assume that each side effect latent feature are associated with several combinations of drug latent feature. So we allow more than one latent combination, not only one. This is for the first problem. And what's the second problem? So we assume that the latent interaction should be spare, and we will control this spare by a sparsity prior. So because we have a spare latent interaction, that means that we can have a high chance to generate spare data, and we can better fit with the spare DDI data. So I will detail a little bit about the computation of spare. So this is I simplify how spare work. So we start with Z and F. Z is for hypergraph representation of DDI data, and F is drug feature, and also maybe side effect feature. And H and B are the latent representation of drugs and side effect, and also the latent interaction. And we reconstruct the graph. And in order to bring the input feature into latent space, we parameterize with two hypergraph neural networks, F1 and F2. And for the decoder, we use Gaussian sampling with the mean values calculated from the tensor product of the latent interaction and latent representations. And we call it the DDI score. And we use DDI score as the predicted drug interaction for each pair of the drug UNV and side effect D. And for sparsity, we control the sparsity by using the spare prior. And we consider three variants of spare. One is for no prior. And the second one is the L1 prior, also called Laplace prior. And the third one is Horseshoe prior, which is the state-of-the-art spare prior. And well, I saw a little bit about Horseshoe prior. Horseshoe prior is the hierarchical distribution with the zero mean. And the idea is they would like to control the variance of this zero mean distribution. And the variance, if the variance is very large, it means the values can be very large and it is far from zero. And if the variance is very small, close to zero, means the value close to zero and it's spare. And the objective functions, we bring the problem into a posterior, and we would like to find maximize the following objective functions. We consider two parts. The first part is likelihood to reconstruct the model, the graph given the latent space. And the second part is the prior. And we just simply use the graph index-based method to do this optimization. Of course, we bring the non-negative constraint for the model. And to help to better deal with the interpretation. So how we can interpret the predicted drug induction from SPARSE model. So we just focus on the all latent space with the drugs latent representation and scientific latent representation. And furthermore, from the latent representation of drugs, we would like to extract associated drugs feature from latent space. We simply use the gradient-based or correlation-based methods. So what's the idea of the methods? The idea of the method is to examine that what happens if we train the, we remove or we switch the protein input feature and observe the change in the latent space. So if we train the protein and the latent space trains very large, it means that the protein is very significant, and I have high chance to associate with some latent feature. So this is a general idea to interpret some latent feature in the deep learning network. And once we can know the associated feature of drug latent feature, we just use them to explain how two drug latent feature interact with each other and to cause side effects. And that's the main idea of our method to interpret drug induction. And in order to show the performance advantage of our SPARSE model, we do experiment. So we use 3 real-world data sets. The first one is to size large data and commonly use drug induction benchmark data from US data. And in the similar manner, we extract to another benchmark data from Canada database and Japanese data. All 3 source of the data sets are publicly available. And we do some filtering to focus on the small molecule drugs. And we use to measure to evaluate the performance, AUC and AUPR. And for train and test splitting, we use 24 cross variation. And this is the result for prediction performance. So we use baseline, which are the molecular graph neural work and the graph neural work on the DDI graph, and some traditional method on the hypergraph. And for SPARSE, we use 3 variants: no prior, L1 prior, and Hosu prior. And we can see 2 things. The first thing, SPARSE without prior, SPARSE 0 is better than baseline in almost case. This shows that modeling multiple types latent interaction is the main factor for high prediction performance of SPARSE. And the second one, SPARSE with Hosu prior achieves the highest performance. This shows that Hosu prior is suitable for SPARSE to control space of latent interaction. And to show some sample for prediction from SPARSE, we show some sample of top predicted interaction with interpretation. So from this table, for the triple here are the predicted interaction, and the 2 columns for interpretation. The interpretation here that the proteins associated with the drug latent feature, and we use them to explain how drug interaction occur. And here is the highlight where our model can extract protein, for example, serotonin transporter and receptor. And we can find some reference for literature support for our finding. And from this table, we can confirm that SPARE can extract associated drug feature to interpret predicted data. And the conclusion of our work. So I would like to bring to a simple conclusion. The first one, we propose a SPARE to encode drug-drug interaction in latent space using hypergraph network as specific controls. And our SPARE model not only achieve high prediction performance, but also can extract associated drug feature for interpreting the data. And I would like to thank for my team, Duc Anh Nguyen, Peter, and Professor Hiroshima Mitsuka to support my work. And also thank you all for listening.
Thank you very much for your presentation. Questions? I'm unfamiliar with the horseshoe prior, so could you explain that a little bit? What that does?
Okay, so horseshoe prior is kind of a hierarchical distribution here. So it's a multivariate distribution with many feature B's. How to and so it follows distribution normal distribution with zero mean. So zero mean means if it's close to zero and all value equal to zero, then it's very sparse, no non-values, and it have a gradient. The gradient allows us to control how the value differ from zero. If it's very large, it means that some feature is significantly different from zero. If the gradient is very small, then the distribution is very narrow, and this collapse into zero, and we have a non-significant feature. And again, how to control this variant, it have two parts. The first part is the global parameter, just to control the global sparsity, tau here. So if we set tau into very small value, then we force the distribution very close to zero, and then we have almost zero feature. And this is an advantage of this horseshoe prior. We can control it absolutely by tau. And the second one is the lambda, which follow the half-Gaussian distribution. Half-Gaussian distribution is a heavy distribution, and it have a main part at the zero. And it for the model a little bit sparse, but it also have a long tail and allow model a little bit have a probability to have a non-zero value. So again, for all of them, this horseshoe prior mainly let the feature shift to zero, and it can allow the model to control how many zero value. So that's the basic.
Okay, thanks. Let me check. There was a question online. Can you apply the SPARSE model for predicting drug synergism?
So it depends on the data and all assumptions. So if the data is sparse and assumption fit with the spare data, then we can apply spare model.